Force and position graphs. So what we're looking at here, within the Unit 8 work energy unit, is a force versus position graph. Now, we already knew that for our work equation, we had something that said work equals a force dotted with a displacement. And remember, this was a dot product, so there's technically a cosine component or a cosine of theta angle in there. But what we're going to assume right now is that our cosine angle is going to be 0 degrees. So instead of writing this as f dot x, let's just say this is a force multiplied by some displacement. We're just going to assume that that cosine is going to equal 1 for now, because we're going to be looking at things from a graphical perspective, and that's what's going to really matter for us in these upcoming problems here. Okay? Now, because this is a force multiplied by a displacement, what we could in theory do is we can in theory think about this in a graph. We could have a force on our y-axis and a displacement, some delta x, on our x-axis here. And if we knew the amount of force then for some amount of distance, we could just multiply them together. So like if we had something like 7 times 4, and we'd see, you know, the answer would be 28. Or although I guess in this case, you know, maybe depending on how this is scaled, that's not a 7, maybe that's closer to a 4, and this would be like 16. Either way, you'd find the area here, because that area equals the work. Now, in our prior problems, we've often said what is the average force, or that the force is a constant. But as we saw back in Unit 7 with impulse momentum, these forces might not be constant. These forces might be variable. They might be increasing, they might be decreasing. The forces can change. So in doing that, we might have a graph where the force isn't constant, but in this graph, it is increasing. This is a linear graph with some positive slope. And if I wanted to find the work that was done here, I'm still just looking for the area under the curve. If I wanted to find out what is the work done through 1 meter of distance, it would be this area. If I wanted through 2 meters of distance, I would need a much larger triangle. I'd need the triangle that comes from here all the way down. So we're still just finding areas here. And unlike our impulse momentum, where we estimated areas by kind of counting dots because we had weird shapes, we could do that in this unit. But because we're just going to stick to nice rectangles, squares, and triangles, the only equations we need to remember are that the area of a square or rectangle is just a length multiplied by a width, and the area of a right triangle is just 1/2 base times height. So with these two formulas here, we can take kind of some funny looking shapes, parse them into different triangles and squares, add them together, and that area is our amount of work, which we could then use for our work energy theorem, where the work is the change in kinetic energy. And if you have no idea what I'm talking about for that, check out our past videos, because we did it there. So let's take an example of what this would look like. And if you ever watched the classic movie with a cowboy and a spaceman, Toy Story, spoiler alert, in one of the final scenes of the movie, Slinky Dog is being stretched on the back of a moving truck as he's holding on to Woody and Buzz, and he's like, I can't hold on, Woody, and then he lets go, and then pshoo, back in, whatever. But what we have here in this graph up here at the right, so we're looking at this variable force graph up here. This graph is a good graph for the force versus position for a spring, like Slinky Dog. What we'd like to do is calculate the work that is done to stretch the spring from 0 to 1 meters, and then from 1 to 2 meters. So if we're just looking for work here, the big thing to recognize is that work is just the area. We're basically asking, what is the area of this graph from 0 to 1 meter under the curve? So what is the area of this purple segment? For part B, when it's asking what is the work, what is the area from 1 to 2 meters, it's really asking us for the area of this kind of trapezoidal region. Or you could think of it as a square with a triangle on top of it. So let's do part A first. If we want the area of a triangle, well, that area there is just going to be 1/2 base times height. So there's our 1/2. Our base, when we look at the triangle, goes from 0 to 1. And this is where you need to be careful because, yes, I recognize that there are 2 boxes here, 1, 2. But I'm not using the boxes as a count. I'm using my axis. And my axis says it goes to 1. So, yes, it's 2 boxes, but it's 1 meter of distance. So we want 1/2 multiplied by 1. That's our base. And then our height here, well, we go up to 1, 2. But that is really at a position on the y-axis of 4. So we have 4 newtons of force there. So we want 4 newtons down here. So this is 1/2 times 1 times 4. 1/2 times 1 is 1/2. 4 divided by 2 is 2. We get our final work of 2. That would technically be Newton meters for a force multiplied by a displacement, which we can also think of work as energy. So let's just call it a joule. You take a second here now. Figure out what that area is for this second region. That orange triangle, square, trapezoid, however you want to think about it. Try to figure out what that area is. Pause the video, take a shot at that, and when we come back, we'll see what we get. Okay, so we're figuring out what this area is. Down here, I have a nice square, rectangle, I don't know. But the base of it is 1, because we go from 1 to 2, so that's really just a separation of 1 down here. And it has a height from 0 to 4, so 4. So 1 times 4, that's 4. This triangle up here, we could do a 1/2 base times height, or we could recognize that it looks to be a very similar square like this as down below, and then we cut it in half, just like you'd cut a sandwich in half. So this area up here is 2. 4 plus 2 is 6. So our work for part B, which is nothing more than an area, is 6 joules. In our next examples we're going to see, we're going to take this idea of the work equaling some amount of area, and we're going to see how an object can speed up or slow down with that work equaling a change in kinetic energy. But for right now, this is what we're going to be doing. This work is equal to an area. That's really what we care about. And until next time, adios, and take it easy.